So this is lesson 2 for unit 4. You'll have to take out your reference tables and turn to table S. We're going to need it in a few minutes, so you should do that now. We are going to be covering mobile bonds, not really chemical bonds, but mobile electrons within a metal. So they're going to be called metallic bonds. And we will also be looking at electronegativity and how it indicates the strength of an atom's attraction for electrons in a chemical bond. The electronegativity values are assigned according to an arbitrary scale, which is on table S. And the electronegativity difference we will be calculating by looking up these values on table S between two bonded atoms. And we use that value to assess the degree of polarity. It's going to actually tell us whether it's ionic in character or covalent. So picking up where we left off for lesson 1, we're on page 7 in the note packet. Metals, this is actually toward the bottom. They're pure substances found to the left of the staircase. As we already know, atoms of a metal do not bond with other metal atoms. They actually share what is called a sea of mobile electrons or valence electrons. Remember, everything deals with the outer electrons, not so much the inner electrons. That would be an absorption of energy where they change from ground state to excited state. That's completely different. That's not bonding. So this allows metals to conduct an electrical current, which we can also call wave energy or electrical waves. So summarizing ionic versus covalent, we're going to visit some animations in a few seconds, but let's fill in the blanks here. So for ionic bonds, electrons are transferred, and in covalent bonds, electrons are shared. And I'm going to show you these animations right now.
Ionic versus covalent bonding. When forming compounds, atoms tend to gain, lose, or share electrons to achieve a stable noble gas electron configuration, an octet of electrons. In ionic bonding, an octet is formed by transferring one or more valence electrons from one atom to another. In covalent bonding, an octet is formed by sharing valence electrons between atoms. Click on one of the compounds or molecules to view an animation of the type of bonding present.
Okay, so we have sodium fluoride here, which is a metal and a nonmetal. So let's see what happens when we look at this animation.
Sodium has 1 valence electron and fluorine has 7 valence electrons. If the 1 valence electron of sodium is transferred to fluorine, both atoms achieve an octet of electrons. By losing 1 electron, sodium has a positive 1 charge. By gaining 1 electron, fluoride has a negative 1 charge. An ionic bond is the electrostatic force that holds ions together in ionic compounds.
So we'll look at fluoride, diatomic molecule. Remember Brinkelhoff?
Both fluorine atoms have 7 valence electrons. If 1 electron from each fluorine atom is shared with the other atom, then both fluorine atoms achieve an octet of electrons. This type of bond is called a nonpolar covalent bond. The sharing of electrons between atoms is exactly equal, and the electron density distribution is symmetrical. The dots in this figure represent the positions of the nuclei. The shaded area represents the regions of space about the nuclei where the electrons are most likely to be. Hydrogen has 1 valence electron and fluorine has 7 valence electrons. If the 1 valence electron of hydrogen is shared with 7 valence electrons in fluorine, fluorine achieves an octet of electrons. Note that hydrogen has only 2 electrons, which is the electron configuration of helium. When bonded to another element, hydrogen will have 2 electrons in its valence shell. In this bond, fluorine has a greater attraction for the electrons in the bond, a greater electronegativity. Because the electrons spend more time near the fluorine atom, the electron density shifts toward fluorine. The result is a greater electron density near fluorine, a partial negative charge, and a correspondingly lower electron density near hydrogen, a partial positive charge. This type of bond, where bonding electrons are unequally shared, is called a polar covalent bond. A polar covalent bond can be thought of as an intermediate between a nonpolar covalent bond and an ionic bond.
Okay, so we're actually going to be looking at polarity in a little more detail in future lessons, not tonight. So let's look at a quick animation of ionic bond.
Ionic bonding occurs between two atoms when one of the atoms has sufficient strength of attraction to remove an electron from the other atom.
Notice how the electrons are mobile.
Has one valence electron with a stable energy level below containing 8 electrons. A chlorine atom has 7 valence electrons. If the atoms collide with sufficient energy, the chlorine atom will remove the electron from the sodium. The sodium atom loses its only valence electron and becomes a positively charged sodium ion. The energy level below now provides sodium with its stable octet. The extra electron completes a stable octet for chlorine, which becomes a negatively charged chloride ion.
And now we're going to look at polar covalent. This one doesn't really have any explanation. So what's happening is here's your mobile electrons. They're always moving, and they're continually sharing those valence electrons. So here only the valence electrons are shown for a water molecule, and it's H2O. So you have 2 hydrogens indicated by the red atoms here, and the oxygen, which is blue. Okay, and what's happening is 2 electrons are being shared amongst the oxygen atom. Okay, because oxygen has a valence number of 6, and hydrogen has to have 2 in order for it to be stable, just like we saw in the animation. So 6 and 2 make 8, so there'll be a stable octet or a stable valence shell for all of the atoms involved here. So this is between 2 nonmetals and mobile electrons constantly sharing with each other. So they're always moving around. So back to our notes. We're going to look at some physical properties here. Okay, so for ionic compounds, physical properties, and remember this is very important, we have high melting point and boiling point due to these very strong bonds. So ionic bonds are extremely stronger compared to covalent bonds. And they are considered electrolytes, which mean that they conduct electrical current in a solution. So when they are placed in water and dissolved in water to create a solution, they conduct electricity very well. For covalent compounds, their physical properties are low melting points or boiling points, and that is due to weak intermolecular forces or forces of attraction between the nuclei and the valence electrons. Non-electrolytes, okay, so they're the opposite, does not conduct electrical current in solution, and they are soft versus ionic compounds, which are hard. So remember, sodium chloride, table salt, it is a hard compound. Continuing on with this box and the differences between ionic and covalent. Ionic compounds have electronegativity differences that are going to be greater than 1.5, or actually greater than or equal to 1.5, whereas covalent is going to be 0 to 1.4. So here are 2 examples, one for ionic, the electronegativity difference. So what you have to do is you have to look at each element in the compound and look up their electronegativity values on the reference table on table S. So when we look up sodium, and you should have it in front of you, look up sodium on table S, and you will see that the electronegativity value is 0.9. The electronegativity value for chlorine, when you look that up, will be 3.2. When we subtract these two numbers, remember difference is subtraction, subtract these two numbers, we get 2.3, which falls above the 1.5 threshold. So if it's above 1.5, it has ionic character. Electronegativity for this one, so here's water, H2O, and we have to look at the electronegativity difference between the two atoms here, between oxygen and hydrogen, because there's two hydrogens. So we only have to do between the one hydrogen and the one oxygen. So when we subtract 2.1 from 3.5, we get 1.4, and that falls in this range here. So the greater the electronegativity, and I'm just going to abbreviate that. Sorry, I slipped on the pen there. So electronegativity difference, what I'll do is I'll just cross it out and make it nicer for you. Electronegativity difference between two elements means that you have a greater percent of ionic character. Okay, and now the closer the electronegativity difference, or END, is to 0, the greater the percent covalent character. You're going to notice that nonmetals have greater electronegativity values. So if you have a bond between two nonmetals which have very high electronegativity values, when you subtract them, the difference is going to be very low. So that means that you're going to have more of a covalent character. So here's our electronegativity scale, and it ranges from 0 to 4.0. And this is what I had discussed last unit. So we're revisiting that, and you're going to see that a lot. So we can classify a compound as either ionic or covalent in one of two ways. Either you look at the elements in the compound, which is kind of gambling, like a trump card, because it's not always going to be the case. But firsthand, it's a good way to classify it. And we did this in class today or on Wednesday. So a metal and a nonmetal is considered an ionic compound. Okay, two nonmetals is going to be a covalent compound. And we discussed that in lesson 1. If you do the math, which gives you a better idea of what type of character the compound has, the greater the electronegativity difference between the elements, the greater the ionic character. This is a summary. And the closer the electronegativity difference between the elements, the greater the covalent character. Again, I'm going to tell you guys here, when the END, electronegativity difference, is greater or equal to 1.5, then it is... Okay, so again, END, electronegativity difference, greater than or equal to 1.5 is going to be ionic character. And then when the END is between 0 and 1.4, then we're going to say that it can be a covalent compound. So let's look at some examples here. I'm sorry, skip that. Okay, sorry about that. So END, we have to figure this out. So we're going to look up the electronegativity value of hydrogen and the electronegativity value of oxygen. So oxygen has a value of 3.5. Hydrogen is 2.1. Subtract them and we get an END of 1.4, which makes it covalent. Calcium oxide, so look up the electronegativity values for each element. So calcium has an electronegativity value of 1.0. Again, oxygen, we don't have to look that up now. So our END is going to be 2.5. We subtracted these two numbers over here. And now, as we look, the electronegativity value is greater than 1.5. So we're going to say that this is going to be ionic in character. So number 3, we have sodium chloride, and then we have to look at the electronegativity values of sodium and the electronegativity values of chlorine, and then we have to calculate the difference to figure out whether it is going to be ionic. So sodium is going to have an electronegativity value of 3.2. Nope, actually that's a mistake. I'm sorry. Sorry. Erase that really quick. Moving too fast here. Chlorine has an electronegativity value of 3.2 and sodium is 0.9. So therefore we subtract this and we get 2.3, which makes it ionic. Again, if you look, we have a metal and a non-metal, so that's going to make that matches up our methods, okay? Both ways. We can look at the compounds and we can do the math. So here, this one's bold for a reason. All right, we have a metal and a non-metal, so you would anticipate that it would be ionic. At least the compound is ionic, but what type of character does it have? What type of bonds or mobile electrons are we dealing with here? So we have to look up the electronegativity values of iron. My pen doesn't want to work tonight. So we have to look up iron, and we have to look up chlorine. Well, we have chlorine, so chlorine's 3.2. And iron is 1.8. Remember, metals have low electronegativity values, so they're going to be much smaller than nonmetals. And when we subtract these two numbers, we get 1.4, which, according to our rules, says that this is actually covalent. Okay, but it is an ionic compound. A little different, okay? H2O2, hydrogen peroxide. So we have two nonmetals bonded together here. You're going to anticipate that it's covalent. So hydrogen and oxygen again. 3.5 and 2.1. Same type of electronegativity difference. Okay, you're only dealing with hydrogen and oxygen. Doesn't matter how many you have. It's still the electronegativity difference that's going to determine what type of character it has. So our END here is going to be 1.4, just like water, and that makes it covalent. And again, that matches up to nonmetals, covalent. All right, so now we have phosphorus and oxygen bonded together. And so we know that phosphorus is a nonmetal. We know that oxygen is a nonmetal. Oxygen has an electronegativity value of 3.5. We look up phosphorus, and that is 2.2. When we subtract these numbers, we get 1.3, which indicates that it is covalent. Number 7, bold. Okay, so we're going to have the same concept here. Okay, same example. What's happening here is we have a metal and a non-metal. So we're going to anticipate that it's ionic, but it's not going to be ionic in character. It is an ionic compound, but based on the electronegativity difference, it is not. So what we're going to do is look up our electronegativity differences. Hydrogen is 2.1. Lithium has an electronegativity of 1.0. Our END is going to be 1.1, which makes it covalent, less than 1.4, but again, ionic compound. I'm going to abbreviate compound here. for you guys. All right, and the last example, and then we're finished for the evening. CH4, which is methane, and we look up the electronegativity values of carbon and hydrogen, and carbon is going to be, well, hydrogen we know is 2.1. Carbon is 2.4, and our END is actually very, very, very close to 0. 0.3 makes it very covalent in character. And that finishes our lesson for this evening.